Hello everyone, I'm Yongzhen Wu from Huawei. Today I'm going to talk about our virtCCA and CoDA. So a bit of background of our previous work. So previously we worked on, I think 4 years ago I came to Ninaro to talk about our QEMU emulation of the ARM CCA hardware. Since the QEMU officially supports CCA, so we have moved our work onto the QEMU itself. So this work is not maintained. So later on, we worked on the virtCCA. So I will first introduce our virtCCA that is using the existing ARM hardware to build the CCA similar to CCA software stack. And then I will introduce our device assignment. We call it CoDA. So a bit of background on the ARM CCA. So we have 4 worlds. The real worlds is what we talked about in our previous talk, is the CCA. And then we have the secure world, so which is introduced in a previous generation of ARM hardware. So before we have the CCA, we still have a long time without the CCA hardware. So what we can we do with this the time duration? So we have introduced the virtCCA for the in the existing ARM hardware. So it's for software compatibility. It has minor modification to the host software and to the Secure-EL2 software. We call it TMM, similar to RMM. And for security, because it's different hardware, so we don't have memory encryption. So the security guarantee is a bit different. So we cannot stop the bus snooping attack and code boot attack. So for performance, I will later introduce it's within 10%. So let me go a bit detail on the memory allocation. Just now, Sobi asked the question of whether the memory allocation is static or dynamic, because the ARM we use the TrustZone, so it's all static. So that means if the cloud provider wants to use virtCCA, it has to be predetermined how big is the secure RAM, how big is the normal RAM. So a little bit of performance evaluation. We run the spec CPU and Unix bench. It shows the average is within 10% overhead. And if you look closely, for CPU intensive job, it's quite little overhead. But for I/O intensive job, it's still quite high. The reason is because for I/O, you need to go through the bounce buffer. So this will bring our incentive to our next work, which is CoDA. We call it confidential device assignment. So the problem to get device into the CVM is that the device sits in the normal world, while the memory, the CVM memory, sits in the secure world. In our case, the virtCCA, it sits in the secure world, so they cannot communicate. So there are 2 ways. The first is to bring the memory to the normal world. If we bring the memory to the normal world, they can communicate, but the problem is it needs to be copied from the normal memory to the secure memory, which is in the CVM. We call it a bounce buffer. So it incurs some performance overhead, and also the host can access this bounce buffer, so everything needs to be encrypted. And in this case, it needs to be encrypted using the CPU resource. And another solution is to bring the device into the secure world, which is the TDISP. But the problem is similar to the CCA, is that we have little CPU support in the market, and we have little device support. As far as I know, there is only one device with the GPU the latest GPU supporting it. So the vast amount of legacy device is left behind. So what we came out with the existing hardware is that the CoDA. So we have a special hardware in the lower, in here, we call PCIPC device, which is, it can switch device from from normal world to secure world. It's similar to the ARM TCPC, but TCPC manages the peripherals, and the PCIPC manages the off-chip PCIe device. So if we look closer to this legacy device support, the one problem is if we want to support the legacy device, we also have to support the legacy driver. That means our objective is we don't want to change the legacy driver code. So for TDISP on the left, the driver is TDISP aware. So the driver is able to do the authentication of the device. But on the right side, the CoDA, the driver is CoDA or TDISP oblivious, so it doesn't know the existence of this. So we have to let the TMM do the attestation. So we call it attestation before the boot, while the TDISP is attestation after the boot by the driver. Let's go a little bit detail into the PCIPC hardware. So there are two, there is a register. If you look at, let me see, do I have a pointer here? There is a register sec equal to 1. If we set the register to sec equal to 1, then this device is switched into the secure world. If during boot the default value is 0, that is in the normal world. So once it's switched to secure world, firstly the host or the host kernel cannot interact with the device. So for example, MMIO cannot go through. And second, the device is able to access the CVM memory through the DMA, because the PCIPC will tag the DMA stream with the secure bit, so that the SMMU will look at the secure bit. It will look up the stream table in the secure world. So we have done it in the for using the GPU for to do inference on the LLM, because nowadays everyone wants the AI running in the confidential virtual machine. So we look at the GPU performance. So it shows the purple one is the bare metal, is the fastest. And for normal VM, device assignment is in the middle, while the CVM is on the right. So there is very little performance overhead. So I'm going to talk about our ongoing and future work of CoDA and virtCCA. So the first is we want to have a confidential container running with virtCCA, and we want this software stack compatible with Kata container. And second is we want to support live migration for virtCCA. So first phase is live migration without CoDA. And third is we almost finished developing it, is SRIOV. Previously in these slides, the register, the sec equal to 1, the sec equal to 0, the register is per port or per device. So it's not per function. So if there is an SRIOV device, we need to either switch the whole device to the secure world or switch to the normal world. We cannot switch a VF. So our current work is we want to support SRLV, the function level switch of confidential device. This is through software. And lastly, because we have this legacy device support, and we want to support disaggregated storage. So in data center, most of the storage of the virtual machine is an disaggregated storage. It's not for example, the disk attached on the host itself. It's on a storage server. So since since CoDA support the legacy DPUs or smart NICs, so we can use this to support disaggregated storage for CVM. So this comes to the end of my talk. If you have any questions.
So in the future work, if you go to that slide, so you are mentioning like this live migration. Can you say few more words about that? What that, like what's your exact idea? How do you perceive it and how do you view it? And what's your roadmap for that?
You mean what is live migration, or
yes,
how do we do live migration?
So what is it?
Okay.
So in my understanding, basically you are saying that there is a running RAM, and you want to move this RAM to some other machine.
Another machine, yes.
Right.
Yes.
And live here means that basically you do not want to interrupt it.
Yes.
So I'm kind of thinking more from the security perspective. What are the security concerns of such a migration? How does that happen? What is the protocol and so on? Is this something in scope or out of scope of your work?
Yeah, it's in our scope. So live migration, we want to so first we don't want to interrupt the work running in the virtual machine, and the virtual machine is from the user point of view, it is not aware of the live migration, and that the work related to confidential virtual machine is we want the measurement still works when it moves from one host to another host, because the trust anchor is different, so we want to still work. So that is most of the work to support live migration of CVM.
So what do you mean when you say that host, the trust anchor is different? So from confidential computing perspective, they don't care who the host is, right? So what do you mean when you say the trust anchor is different?
The trust anchor is in the CPU, so the cryptographic key is in the CPU, right?
But the user also doesn't care about that.
If you move to a different CPU, the anchor will be different. But they will be signed by the same authority, but the hardware is different.
But typically so how do you, so identity is not a part of attestation, so I'm struggling to see what do you call as the identity. Can you, it's only changing from one host to another, and if you trust both public keys, so
okay.
I'm trying to understand what's your kind of, how is the user going to know that something has changed? Maybe put it this way.
This live migration for confidential virtual machine is not a new thing. So if you look at the TDX and SEV, they have their live migration standard, and we are not trying to invent new things in it.
Right, but maybe my question is not that whether someone else is doing it or not. My question is to understand what exactly it is. But maybe we follow up later on if maybe some other people have questions.
Just a quick comment on that, and then I've got a question. Just to say that live migration is in scope for the next version of the RMM specification that ARM's producing, which will define the flows here. including the security concerns and how it affects the attestation, the platform attestation report and the activity log that the realm can inspect and, decide whether it trusts the migration or not. That's not available yet, but when it is, then I guess virtCCA can pick that up as well. My question, so you have this kind of special hardware to switch between secure and non-secure worlds. I'm just wondering, is there some kind of automatic scrubbing of device state when you go back from secure to normal world?
Yeah, a good question.
Things like that.
Yes. So, there are a few problems. So first is if the device have a state, especially have a persistent state. For example, it's a disk. Then we still need to use the disk encryption. It's either software encryption or SED. And second, if the device doesn't have a persistent state, let's say it's a network card, so there's no need to scrub the network card. For network card, then there are two different kind of network card. First is the DOM network card, where you cannot flash firmware. And second is a smart kind of network card, where a malicious host can flash malicious firmware in it. So in the later case, when we switch from normal world to secure world, because we don't know what the hosts have done to the network card, so we have to reflash the network card. I don't know whether I answered your question.
You got me thinking, though, that this problem of legacy devices is not going away, even when there is CCA hardware. There's still the long tail of devices to fix.
Yes.
So there may, maybe not exactly this, but there may need to be more work generally in the ecosystem to sort of stitch together legacy devices in some better way.
Yes, that's the problem. We want to. So for the whole line of work, including virtCCA and CoDA, is we want to use legacy hardware to do confidential computing. Of course, there are problems, especially security problems, for example, with encryption and authentication. And so we are just trying to do our best to use the legacy hardware.
So maybe as a TE person, people always told me that you put your TCB in TrustZone and non-TCB. So I wonder, how is your view on this whole who the attacker is, right? Because if you stuff a whole lot of code in TrustZone, it's not really TrustZone anymore.
Right.
So, for example, or maybe the question is, what do you gain in security compared to a type 1 hypervisor? I suppose that's the major question.
Okay. I think this is a very general question on confidential computing in general, not particularly to CCA or virtCCA. So,
well, I mean, I don't see that much value in, for example, non-memory encrypted CCA. So, I mean, I get that with the memory encryption, everything is nice and fun, and you can define the attacker. But if you put it in TrustZone, you get less guarantees, right? So.
Yeah, when you talk about TCB, is the amount of software you need to trust. It has nothing to do with whether it's encrypted or not. So, for example, if we stuff all the gas virtual machine inside the TCB, it's big, but it's big for CCA, it's big for TDX.
Yeah,
it doesn't matter whether it's encrypted.
Sure, but I meant memory encryption. But I get the isolation point of the memory encryption, but you don't have the isolation point of the memory encryption. So this is why I'm asking, is that who is the attacker in your case? Who are you trying to protect against?
Okay. So our attack, this is about our adversary model. So the attacker first is the host, and which is in general the adversary model of confidential computing. So we don't trust the host. And the only different part of the virtCCA to the general trusted computing is that we don't have memory encryption. So if there is an attacker to open the box and snoop on the bus, then we cannot defend that. We are working on some workaround with this attacker. We try to use the intrusion detection of the casing. So for the casing nowadays, it's quite common to have the intrusion detection to say the case is previously opened. So we try to link that information with the TPM so that when the case is open, the TPM key is erased. But this is an ongoing work.
I think there are HSMs that do that. But I mean, the problem is in your CVM, you're essentially running third-party software. So by definition, it's not TCB anymore, right?
I'm sorry.
So your CVM is like a full-blown Linux kernel with lots of stuff.
Yes.
So it's not TCB anymore, right?
The CVM is part of the TCP. You have to trust the CVM.
I don't think anybody in this room says... It's a bit messier. The CVM is the thing you're trying to protect. So one CVM just needs to trust itself. You've still got isolation between the different CVMs because it's classic virtualization. So you don't need memory encryption as such. You just need to make sure that anything that moves out of that state and moves into normal world is wiped while it happens.
Yeah, sure, but again, my question is, how is it better than type 1 hypervisor?
Oh, so is that your question on whether a malicious CVM can attack another CVM? Is that your question?
Yes, or the TMM,
oh, okay.
whatever.
Okay. So this adversary model is not part of the confidential computing, but confidential computing have to follow that. This adversary model is for general virtualization, right? So in general virtualization, one VM cannot attack another VM, and the one VM cannot escape from the VM. That one we still hold. And
it's a fair point. If you end up with a state where you can make a type 1 hypervisor that is as small as, say, the ARM in CCA or the TMM here, you're absolutely right that there's no fundamental gain. The difference is that what you're trying to do is move a lot of the stuff that's complex but not necessary for the TCB. You're leaving that in the normal host kernel. So you can get the amount of code in that one component considerably smaller. If you can't, the whole thing's a bit pointless. So hopefully we can.
Yeah, in the full CCA model, the whole idea is the RMM is almost entirely architectural, and there's no special weird drivers, and you've got expectations around what the hardware looks like. So that makes it a lot simpler.
So in this case, what happens to the traditional secure world software? Is that all displaced for...
Okay, you mean the traditional TrustZone software, like the OPTE, right?
Yeah, all the secure
okay,
services.
yeah, good question. So we do have this question in our real product line. So they still want the traditional OPTE inside. So we don't have a very concise solution yet. So one way is to run it in one of the CVM. So we have to port it to the CVM. The other is we have to run it like a virtualized SEL2 that we don't have a concrete solution yet. Thank you.